All right. Well, thanks to everyone for coming. I hope everyone had a good weekend. Here in the U.S., many people had a very um, celebratory weekend. Um, um, so the three things I wanted to just touch on briefly. So, first of all, the construction that Mike and I are working on right now to um, generalize um, Christian's construction, we landed on an investigation of a functor that replaces the functor to poset, so which takes sets um, and produces the subset. So that's a poset like construction, and part of that is motivated by the fact that in poset there's only one morphism between any two objects, which means if you want to model proofs, your proofs collapse. So that's less compelling from a certain perspective. So as I've mentioned, one of the things that we've been doing is looking at sort of V-enriched categories. And when you do most of this construction, the V structure pulls through. But when we want to go and do some analog of sub, the question was, can we use the tensor to do that? And it's not immediately obvious unless you impose some additional constraints. So let me see if I can. All right, so here's an article that describes the the categorical version of Girard's geometry of interaction program. So originally what he wanted to do was to give a model of proof reduction. So as some of you who have been following me may recall, in intuitionistic logic, there's a rule called the cut rule, which is basically applies an implication to the hypothesis, resulting in the consequent, right? So you have A implies B, a proof of A implies B, you have a proof of A, so you apply A implies B to A to derive a proof of B. So rules that, proofs that involve the cut rule can be turned into proofs that don't have any cuts. So that's a result called a Hauptsatz from Gensen's sequent calculus. A similar kind of rule exists in linear logic. You have a cut rule, and there's a similar kind of proof normalization. So Girard spent some time modeling proofs themselves, and he's gone through a variety of different mathematical objects that represent proofs, and has given what's called the execution formula, which is an interpretation of the proof normalization. Now it turns out that you can give a categorical interpretation, and the execution formula is closely related to composition and what's called the int construction. So in the int construction, you start with some symmetric monoidal category, and then the new category is taken from pairs of objects, and the morphisms run forward, sort of left to right, the outer pair, and right to left in the inner pair, in the outer. So if you're trying to, so if you have a morphism, then the morphism runs from two pairs, right? An A plus and an A minus to a B plus and a B minus. So the outer morphism runs from the A plus to the B minus, and the inner morphism runs from the B minus to the A plus. I think I've got that right. You can check the tutorial I just linked. So that's the basic construction. Now, if the monoidal category is traced, then the trace is what gives you the composition. So you can think of the trace as like a one way to think about this kind of composition with the trace is, and this is sort of the typical style. If you think of your morphisms as boxes, then, with wires coming out, A plus running out to A minus, and similarly for the B line. Then when you wire up an A to a B and a B to a C, you have the possibility of running directly from the A out to the C, or you run from the A out to the B, and then you go over into the other box and come out and back through the B and loop around as many times as you need until finally you have a B to a C. So that's kind of the way so you can think of the trace as providing you the looping until you exit semantics. That's what the trace is doing for you. It's easy to visualize, and maybe that if you look at the tutorial, you'll see that. I might be able to screen share it so people can see what I'm talking about. Let me see. Hang on. Okay, so can everyone see this diagram here?
Yes.
Yes.
Okay, so if we arrange the morphisms as boxes, then notice that the polarities for the A's and the B's are reversed, right? So a morphism from an A to a B flips the B's around. And that's important for composition, right? So suppose that you come in this way and you can go directly out through the B plus to the C plus, right? So that's one path. But you couldn't, so in other words, there's a direct path essentially from A plus to C plus, right? So that's one way. However, it may be that you come out from the B, but you loop around several times. So the B plus, because these are flipped, right? So then the output here matches the input here. So you can come in on the G, and now you'll come out on the B minus, right? And so you can, that B minus matches the input for the A, for the F, right? So you can come back in. So you go around this loop as many times as necessary until you have an exit condition that'll get you out here. So this is the formula for it. So you can just check that the formula lines up with the diagram, which I won't do for you, but you can check it at your leisure. So this is the approach to composition. So anyway, so this kind of category models the cut elimination, or allows one to give a model of cut elimination. Now, in order to have these traces exist, you can build a canonical trace if your category has two properties. So it has a tensor product and it has what's called a unique decomposition. So you can take your tensor product and write it in terms of its factors. So think about this as like the unique factorization theorem for multiplication. So that's kind of that's one way to think about this property. And if you have this unique decomposition, then you can build a canonical trace. And sort of the canonical trace, I think they've got it here. Let me see. It's easier to understand in the yeah, here it is. Yeah. So here's your what they call the standard trace formula, or a canonical trace. So if I have an F that has it goes out an X and a Y, and it also has a U along the side. So think of it as X in terms of your boxes. X comes in, Y comes out the bottom, U comes in the top, and U goes out the bottom. So you can now think of this as getting rid of. So either you go straight from X to Y, or you loop around as many times on the U parameter as you want, and then finally come out on the Y. So you've got a box. There's an X part and a Y part, and there's a U part. So either you go straight down, or you go out the U, you come back in the U, and there's a loop around some number of times until finally you can come out the Y. That's what this trace is doing. That's exactly what this formula does. And you get that from the kind of the unique decomposition property. So that's what you and there are lots of examples. So rel under disjoint union, partial functions and partial injections under disjoint union. There's a similar lifting of that kind of construction to a stochastic situation or to a more quantum-like situation. All of these are examples of traced categories with this unique decomposition. So the point about this property is that now if we insist that our V, so if we wind back to the point before, V is some V-enriched, or sorry, V is what we're modeling as our collection, right? And so we're insisting that we're taking account of our formulae in some V-enriched encoding. So for example, the theory, the Levere theory is V-enriched. So the Levere theory is the gadget which is modeling the structural connectives for our notion of computation. V is going to be our notion of collection. Now we're insisting that V is monoidal, right? So it's got something like a disjoint union or some other kind of way of aggregating things. And then we insist that it has a unique decomposition. Then what we want to do is we want to construct something that's equivalent to a power set, but isn't going to be exactly the power set. But what you can do is you can take the tensor of all the factors, which will be larger than the larger than just the factors, right? Because you'll have duplicate entries for the factors. When, so for example, in the case of 60, right, you've got lots and lots of factors, right? So you've got 2, 3, 5, but they occur, 4 also divides 60, so it's like, so 4 times 3 times 5, right? That's 60. So 4 times, so 2 will show up, 2 times 3 will show up, right? And so when you product all the factors, that will be larger than 60, if you understand what I'm saying. So the same thing here, when you tensor all the factors of the tensor, you'll get something that's much larger than the original object. And that new thing is a stand-in for, or an analog of, the power set. And that's what we're trying to construct. Now there's a couple of different paths you can go down this. So one of the things that we're investigating is also, when does the monoidal construction arise from, or is directly connected to, a monad? And when that's the case, then you can apply the unit of the monad to the factor before you tensor it up. And when you do that, then then the whole construction reduces back to the power set. So I want to investigate that so that we can have this bridge between the two different concepts, right? We want to be able to show how this power object that we've constructed is like the original power set. So there's another kind of wrinkle, because when we take this sum of, or when we take the tensor of the factors, we don't get a V of V's in the same way that the power set is a set of sets. So that's a typing sort of mismatch that I also want to address. So I'll have to think about how that plays out. But that's essentially the path of the construction we've been looking at. I know it's a lot of information, but I'm wondering if this makes sense to folks.
It's a lot of information. But,
yeah. So if you recall, is that all of it pieces together rather nicely. So ultimately, what we want to do when we develop a logic from the in this operational semantics and logical form approach, we want to be able to model not only the formulae, but the proofs. And so understanding how proofs get modeled is important. And a lot of what's going on in this tutorial that's on the screen is the mathematics that's necessary to model the proofs. And in particular, what we're interested in is that when we generate the logic, we're not tied into a notion of collection that can't handle the linear logics. So if that notion of collection doesn't allow us to generate the linear logics, then something has gone wrong with the account. And so the idea is to relax the constraints on the collection. So rather than it be just a, rather than it be set, we just want it to be rich enough to have a notion of aggregation. And that's essentially some kind of monoidal construction, right? So when you append two lists, right, that append is like the monoid product, right? Where the empty list is the unit, and obviously append is associative, right? So this, the union of sets is clearly the same thing, right? So the union with an empty set is just the set itself, and the union is clearly associative. So that's a monoidal construction, right? So we're just asking that V support some kind of monoidal construction. But we're also, in order to build this a gadget that is like the power set, right? So power set is very clear. We understand what power set is, even though it has its own mysteries to it, right? We don't know how fast it grows. In fact, its ability to grow is independent of, or how fast it grows is independent of the axioms of set theory in general. Right, that's the continuum hypothesis. So we want to build something that, so we're trying to follow sets as a guide, but not be as concrete or as specific as sets in terms of our notion of collection. So the monoidal structure is what's giving us something that's like union, but not the same as union. And we want to build something that's like the power set, but not the same as the power set. So if we insist that the monoidal product has a unique decomposition, then we can always find the parts of any object, right? The parts are the factors of the monoidal product. So every object in the category is going to be represented by some monoidal product. And we're going to insist that always come with an inventory of the parts. And then we want to assemble the parts into an object. Well, the only thing we have available to us to assemble is the monoidal product. So we take all the parts and we assemble them into an object. So this is following exactly the power set construction, but without all the extra information about sets. Does that make sense?
Yes.
Okay.
Yes.
So that's essentially what we're doing, and we're doing it in such a way the reason we're relying on this unique decomposition idea is because we want to be able to model linear proofs. Right, so this unique decomposition approach, this traced unique decomposition categories, gives us a natural way to model linear proofs. So if in providing our collection semantics, we have followed not only the way set works, but also the way these unique decomposition categories work, then our proofs should share that structure. That's kind of the idea. So that's the high level. So we don't want to just model formulae. We also want to model proofs. That's the key idea.
So am I understanding this correctly? You are saying that you already said that set is not enough as a collection, and you also mentioned the graphs are the first next step. Are you saying now that you don't really need the graphs, but a set with this additional monoidal?
It's not necessarily a set. It's some category. So right. So we were looking at graphs from the point of view of any structure that is entirely ordered. When you ask for all the parts, if it is possible for some parts to be disjoint, if there's a separability property in your total order, then those separate pieces will be unorderable with respect to each other. And so you have to be able to model that partiality. So you at least get trees if you allow that sometimes, two things can have the same part, or two things can come from the same parent, then you'll get graphs and not just trees.
Mm-hmm.
Right. So that's, but now, so that's very concrete reasoning, right? We're saying specifically what the structure needs to look like. But you can also work from the other side of it. You can say abstractly, without knowing the inner bits of the thing, just what is the monoidal, what is the aggregation mechanism. And what we're saying is it has to be, at a minimum, it has to be monoidal. Now the graphs support a monoidal product.
I see.
Right. But at a minimum, it has to be monoidal, and that's our way of gathering up parts. And now in order, so the thing that's interesting about sets is that they have a, you can find all the parts, right? It's basically all the elements of the set. And then you can reassemble the elements in bits and pieces. So that's how you generate the power set. So all we're doing is insisting that instead of elements, we're asking that there be, you know, a unique way to decompose the tensor. Right, you need to be able to get it down to the atoms and their repeated use. Then you can reassemble all of the parts in using the assembly mechanism that you've got, which is the monoidal product. So all we're doing is just literally, you know, just following the blueprint of sets. Now we can apply that blueprint to graphs. Does that make sense?
Yes. Yes.
Cool. Yeah. So that's the idea. And what the other thing that we're insisting on is that sets are not the only thing that's providing the blueprint. The other thing that's providing the blueprint is the mechanism by which we can model linear proofs. So that scheme is there so that we can not just model the formulae, but we can model proofs. That's the idea.
And when you say model proofs, can we say that proofs are programs and modeling proofs are executing programs? Or
that's correct. That's correct. But what you want to do is you want to give a direct interpretation. So it's not necessarily the case that the mathematical objects that you use to model these proofs look like programs in the first place. But later you'll discover that it's rich enough to give you a programming semantics.
oh, I see.
Yeah.
And with a monoidal product, you're talking about total ordering and decomposition. And you said that
the point is that you can't have a total order. It's not possible, right? That's essentially why list fails. So you can have lists of lists, but you can't uniquely generate the list of all sublists of a list.
and inside, so we don't have total ordering, but we have ordering in
you have a partial
in each piece.
Yeah.
And partial order means inside each piece, or what exactly
the main thing, suppose I have the list 1, 2, 3. So I have the list 1, the list 2, and the list 3, right? Each of those are sublists. So how do I order the list 1 with respect to the list 2? Or how do I order the list 1, 2 with respect to the list 3? Which one comes first in the lists of all sublists?
We can look at elements.
Yeah, and
And
So for example, which comes first in list 1, 3 and list 2, 3? Which comes first in list 2, 3 and list, sorry, list 1, 2 and list 2, 3?
I see. We can look at the elements, but it can be a situation where, yeah.
Yeah, that's kind of the point is that there's no canonical way to do this. And it, yeah.
And with the monoidal product, how we can do this?
So the monoidal product is giving us partiality, right? It's not insisting that you have an order. In fact, that's why we're assuming that we have a symmetric monoidal, right? The symmetry is the lack of order.
This piece is not really clear to me.
So
I'm thinking about ordering.
In the same way that in set, right? Union, the set 1, 2, 3 is the same as the set 2, 3, 1. Right? And A union B is equal to B union A. So that the union is symmetric.
Oh, so this means that the set is like something that we it's nice for that, but it's missing something. So we need this additional like monoidal product to be able to.
No. The thing that's the monoidal product is not in addition to set. The monoidal product has a direct interpretation in either in terms of product or in terms of disjoint union. All of these examples are all variants of a kind of disjoint union. So for example, here, rel plus, right? So it's category of relations in disjoint union, disjoint union. So that's the monoidal product is the disjoint union. And obviously disjoint union is symmetric. Even if you do, you can always switch the tags. So since you can always switch the tags, there's a symmetry map. And that symmetry is what's erasing the order. So the monoidal product is not additional information to set. It's an abstraction. I'm saying I don't want to think about sets. I want to think about this generic gadget. And the reason we want to think about this generic gadget is because sets will always generate a Boolean logic. They won't generate a linear logic. So if we want the collection to be the thing that's responsible for generating the logical connectives as opposed to the structural connectives, then we need something else, something that isn't set. Does that make sense?
Yes. I'm thinking that I need to better understand monoidal product and how in relation to sets.
Well, I mean, in this case, it's literally just disjoint union, right? So A plus B is the same as the union of tag everything in A with a 0 and tag everything in B with a 1. So now you take the big union of that, and I can always get back the things that were in A because they're all tagged. And I can always get back to things that were in B because they're all tagged. But I can also flip it around. I can do B plus A, and all that does is just it flips the tags. So the A's are tagged with 1s and the B's are tagged with 0s. So you have a symmetry map, right? Mm-hmm. The symmetry map just flips the 1s and the 0s. Like it doesn't even inspect. It doesn't even need to know whether it whether it's an A or a B, right? It just flips the ones and the zeros. And that will automatically get you B plus A from A plus B.
I see.
Yeah.
I remember you were talking about this in the lecture of Introduction to the Design of Computational Calculus.
Yeah.
With
Yeah.
the tagging. Yeah.
Yeah. So yeah, tags are tagged unions are the monoidal product here in these examples. I mean, it's a little more sophisticated in SRL and HILB too, but it ultimately it's really just a variant of disjoint union. All right. Well, I guess it's time for Dev stand up. So I'll see you guys over there.
Okay.
See you. Thanks.
All right.
Bye.
Thank you. Ciao.